All right. Hello, everyone. Thank you for joining DataCon LA 2020. Welcome to the Data Infrastructure and Security track. And soon we'll be listening to the session Data Warehouse or Conventional Database, which is right for you, with our speaker, Robert Hodges. I am Nilesh Tiloda, your host, and our co-host today is Sachin Nahar. We will be moderating the chat and Q&A for you during this session. Robert will be talking about data warehouse or conventional database, which is right for you. A quick intro about Robert. Robert is the CEO of Altinity, a software and services provider for ClickHouse data warehouse. He is also a database geek who has worked with over 20 different database systems. He leads the San Francisco ClickHouse meetup. Without further ado, I'll hand this over to Robert. Thanks for being here, Robert.
Thank you, Nilesh. It's a pleasure. And I just, before I do anything else, I want to give a big shout out to you, to Sachin, Subhash, and the whole team for putting this conference on. I love DataCon LA. It's not just a great logo, it's a really great conference. So it's wonderful to be here. All right, so as Nilesh said, we've got this topic, data warehouse or conventional database. We're going to dig in and find out which one is right for you. So just a little bit on the background here. So Nilesh already gave my bio. I do business stuff over the last year and a half or so because I'm running the company, but I'm really a database geek. I've been programming since I was a kid, starting in 1972. Our company specializes, basically markets ClickHouse data warehouse. We'll tell you a lot more about that in the course of this talk. But in addition to building a business around it, we are a major committer. ClickHouse is an open source data warehouse, and we're also a big community sponsor. So we do lots of events around the US and Western Europe. DataCon LA is just one of them. So with that, I'd like to just dive in and talk about the basic question that we want to explore today, which is, you're a dev, you're building an app, it's going to store data. What kind of database do you need? So this picture here just shows a simple example of an app you might be building. Maybe you have like a Node.js app server, so that's running in the back end. You got React running in the browser. And then this is going to be generating or manipulating data. And one of the big questions is, what kind of data store do you connect to the back end to be able to store this data and access it quickly? And as anybody who has any knowledge of databases knows, there's a bunch of choices. There's everything from graph databases to document databases to SQL relational databases to data warehouses and others besides. What we're going to do is just restrict that choice to two important types of databases today. One is what I call a conventional relational database, and you're going to hear me use the word row store, because that's basically how the data are stored. The other kind of data warehouse or database that we can choose from is called a data warehouse. You're going to hear me use the term column store, because that's, as it turns out, how the data is stored in most data warehouses. And so what we're going to do is explore this choice. And I'm going to make the assumption that if you've used databases at all, there's a pretty good chance you've used a conventional relational database. So we won't spend too much time on that. We'll spend more time on the data warehouse so that we can explore some of the things that are really different about it compared to other database types. So that's the question we're going to answer. And so what we'll do is we'll start with the row store. And since this conference, people here love open source, I really like open source, I'm going to use MySQL as the example database and talk a little bit about its properties. I used to work with MySQL a lot, and of course it's a tremendously popular database for storing data. So let's just start with some top-level properties of MySQL. If you've ever used it, you're probably aware of most of these. So first of all, it's just a single binary. And one of the things that's really wonderful about MySQL is you can just say apt install MySQL server, and within about 60 seconds, if you have a good networking connection, it's up and running. It speaks SQL. It uses row storage, and we're going to dig into that a little bit. But what that basically means is every time you've put a row in the database, all the cells in the row are going to get stored in the same location. And along with that, I have sort of a kind of marketing picture. On top of that, we use a lot of indexes, and we'll look into those in just a second, but the basic data layout is rows. It's also built for high concurrency, and this is a particular strength of MySQL. It is possible to build systems with MySQL that can easily support thousands of concurrent queries. And one of the ways that it does that is the queries are single-threaded. So each query is pretty lightweight, doesn't use a lot of resources on the CPU, and leaves plenty of room for other queries to run at the same time. MySQL is by and large a single server for the data. There are ways to scale it out, for example, using replication, but you're fundamentally going to be connecting to a single server to run your query, and you can't take advantage of multiple nodes. And then a final thing is open source. It uses a GPL v2 license, which is very flexible. About the only thing you can't do is stick it in software that you're shipping. So, but other than that, you can pretty much do anything you want, and there's huge systems built on top of MySQL. For example, a good chunk of Facebook runs on MySQL. So this is a really powerful database, and has been very popular for a couple of decades. What I'm going to do now is let's look at an example and just review how you would build an application that stores data in MySQL. So what we're going to typically do is, and I have a sample application here of airline flight data. This is a data set that's published by the US government. We use it a lot for demos. It's a really fun application, and it basically has a row of data for every time that a commercial airliner flies from one point to another. So for example, if Southwest Airlines flies from Oakland to LAX, a row gets put in the database. It's called the on-time database. And this is an example of how you might design it in MySQL. So you would have an on-time table, and that has all the rows consisting of all the records for all the flights. And they have things like the flight date, the carrier ID, what time did it depart, how much was it departed as well, and additional information. So everything is relevant strictly to the flight. And then what you'll typically do in MySQL is you'll have multiple tables so that you avoid duplicating data. So for example, we will store information about airports. So we have an origin airport and a destination airport. We're going to store that in a separate table called airport, and that's going to have things that are specific to the airports. We have a table that stores information about time because we might want to ask different questions about that. We have a table for the carriers, so on and so forth. And the tables themselves, we have a primary key. And what I'm doing here is I'm using a pretty standard approach, which I have an ID value, which is just an integer, which we can use as the key for the record, so it's easy to join on them. So if you've used relational databases at all, this will look really familiar. What's interesting is as we dig into this and look at what's actually happening under the covers. So if we go ahead and look at the next slide, we'll see how what's actually going on structurally inside this on-time data. So as I said, this the data is stored in rows. So you'll find this if you could go in and look at the InnoDB table space where this is typically stored, you would see that each row is stored and is collocated, all the cells are collocated. Moreover, there's a really important structure which is called a clustered index that allows us to find the rows by ID. So in InnoDB, the rows are ordered by the ID, and then there's an index built on top of it, a B-tree index, that every time you look up a single row, it's going to just walk down this index and land right at your record. And it's called a clustered index because what it means is that the data is actually included in the index, and therefore the table is ordered the same way the index is. This is a really important principle that not every relational data warehouse uses exactly this form of indexing or table ordering, but it's very common in MySQL. Moreover, there's another thing that is shared across almost all databases, is that you'll tend to have what are called secondary indexes. So these are additional indexes that allow you to find particular rows quickly. So for example, if you want to look up something by carrier, find the flights today, on today's date for Southwestern Airlines, you will set up a carrier ID index because that allows the query optimizer to quickly find those rows. And so so what that means is the storage is set up to access, is organized by rows, and it's set up to access rows. There's one final thing that's really important about this, which is that the table itself, if you don't have an index and you're looking for something in the table, you'll just read the whole table. This is called a table scan. And what that means is if you just wanted to find something like the unique flight numbers, for example, which you might not have an index for, you would end up scanning the entire table and reading every single cell in every single row. So for answering questions like that where you don't have an index, it's horrendously inefficient. And in fact, when we look at MySQL and using relational databases in general to store data, they have some peculiar strengths that have made them very popular. So where MySQL really shines is for what we call online transaction processing, or just transaction processing for short. And that means that, for example, we're running an e-commerce site where, or a website where we have lots of lookups. We may have a lot of quick updates. For example, people filling out their, filling up their basket as they're perusing and buying things. They have very high concurrency because many people may be operating there or using the site at once. A final thing is there's a lot of effort that goes into ensuring that the data is very consistent, because if you're selling stuff in an e-commerce site, having things a little bit wrong is really bad because you're losing money, you're causing people's transactions to fail, you're giving people a bill that's not correct. These are really important to get right, and MySQL is optimized for it. So when you're using MySQL, it handles all of these problems really well. And in fact, the performance is really astounding. It's not hard to build, to put together a MySQL server that will hit a million queries per second. This was cutting edge 10 years ago. Nowadays, it's just it's really easy to do. The flip side, though, is there's certain problems that MySQL handles very poorly. And they are problems where the tables, for instance, where the tables become huge. So that this flight data set we're dealing with has about 173 million rows in it. That's beginning to be a long table. Tables that are very wide, that have an enormous amount of information in them. Tables where you ask open-ended questions where there's no index. And then finally, tables where you're doing what are called aggregates, where you're totting things up, like number of flights per day, the number of flights that were delayed by more than 20 minutes by carrier, by month, by airport. So these are things that MySQL is not particularly well suited for. And in fact, as you begin to edge into this type of problem, and if this is what you're trying to solve with your application, MySQL is actually not a good choice. So what we'll do now is see what might be better. And for that, what I'd like to do is dig into the column stores using ClickHouse as an example. So a similar review for ClickHouse. Let me give you, in fact, a little bit of history. ClickHouse was originally developed by Yandex, and it was developed to do web analytics. We'll talk about this at the end. I'll show you a concrete example of this. But it was originally developed, started as a prototype in 2008. Yandex developed it, used it internally for about 8 years, and then they open sourced it in 2016. It's since then become extremely popular and is actually used worldwide, very heavily in Eastern Europe, increasingly so in the United States and North America and South America, and then also in Asia. It, in some ways, has superficial similarities to MySQL. It's a single binary. So again, like MySQL, you can just say apt install ClickHouse. It'll come down and be running in 60 seconds. It talks SQL, but it quickly departs, because instead of storing things in rows, we store them in columns. So you can think of each column being stored as a big array. Moreover, that array is compressed. And there are these operators that you can apply called Codecs, which do transformations on the rows before they're compressed. We'll see an example of this and how this can help improve storage. Another big difference is they use what's called vectorized query execution. So they're very efficient at breaking up the operations on these columns, farming them out to all the cores on the CPU, and then also use what are called SIMD instructions, so single instruction, multiple data. These are instructions that, for example, on Intel architectures that allow you to process multiple pieces of data simultaneously in a single register. Another difference is that they're MPP enabled. That MPP stands for massively parallel processing. And what that means is they allow you to spread shards across a bunch of nodes, have those shards be replicated, and then ClickHouse will take care, when you run your query, will enable you to build queries that go and run across all shards and allow you to apply the power of multiple servers simultaneously. And then finally, one major feature, ClickHouse is open source. So it's under an Apache 2.0 license, very flexible. You can use it for practically any purpose you want, as long as you acknowledge the license. So let's look in a little bit more detail here. So in MySQL, I just showed you a picture of the table. In ClickHouse, I'd like to show you the actual data definition language. So if you've used MySQL or Postgres or any other relational database, this will look somewhat familiar. The data types are a little bit different, but it's basically a create table definition. In the airline database, the table's name is ontime. I'll just draw your attention to three things. One is there's this engine called merge tree. So ClickHouse uses engines. It's a bit like MySQL. It's just that the engines are much bigger. Oops, I'm just checking the chat. By the way, if you have questions, feel free to log them in the Q&A. If they're relevant and I see them, I'll handle them as I go by. Otherwise, we'll have time at the end. So this engine is just saying, we're going to use an engine to organize our data called merge tree. And merge tree is the workhorse engine for ClickHouse. There's about 40 of them, or maybe 50 by now. They all organize and manage data in different ways. Merge tree is the main one, and there's a family of engines that have different variations on it. It has a couple of important properties, which is a partition by, which means this is a way to break up data. We're going to break it up, as it turns out, by day, and we'll see what this looks like in the storage. And then ordering. So in data warehouses and column stores in general, we tend to order data because it makes it faster to find it, and it also makes compression more efficient. And then finally, if you look up, and you'll see this funny keyword codec. What this does is allows us to control the compression in the codecs. By default, ClickHouse compresses all columns using LZ4 compression, which is pretty good compression and doesn't take a lot of CPU time to do the compression when you're inserting data. But we can use this codec keyword and we can tweak that. So for example, to use what's called a codec, which is a transformation that applies before the data gets stored, and then use ZSTD, which is a more efficient but more expensive form of compression. We'll come back to that and show actual examples. What I'd like to do now is just show you what the layout is in storage. And this is a picture that shows you how the tables are organized in storage. And there's a number of things to notice. One is, as I said, the data are stored in columns. If you go and look at ClickHouse on disk, you'll just see for every column, you'll see two files. And then you'll see some additional files, including one called the index. So primary.idx. And what that is it's a sparse index that just contains a bunch of whatever your order by is. We call that the primary key, but it's not there for consistency. It's just to locate data quickly. And it basically will walk the ordered values of that primary key, and by default, about every 8,000 values will have an entry in the index. This is called a sparse index. And the reason that we have so few entries is it means the index will always fit into memory, even when the table is enormous. And so when we want to find data and the database recognizes it can use the index, it'll just search this index, it'll find particular groups of rows that it wants to access, and then it will walk over to the columns, and the columns basically have one array that links the rows to points in the, to blocks of compressed data. And then the other file for each column is just the blocks of compressed data themselves. So in data warehouses, not only are things ordered in arrays, but we're optimized to just do brute force reads on the on these columns, doing it as quickly as possible on compressed data. There's one final thing. If you're looking at this, you'll notice I don't mention indexes. ClickHouse has indexes, but it actually doesn't need them a lot of the time. So I'm not even going to talk about them in this talk. But if you do find that the indexes, though, they function a little bit differently, what they do is they allow you to knock out things so that as you're scanning these columns, you can avoid reading parts of the columns. So that's how indexes work in a column store. It's very different. So one of the things is that we can now, with this background, start to see why column stores perform well on particular kinds of queries. So one of the big things is there's no longer a penalty for having wide tables. The database table that we were dealing with ONTime is 109 columns in the data warehouse. We've actually denormalized it, and we can afford to do it because if we do a query that reads 3 columns, we're only going to touch about 3% of the data on average. So there's virtually no penalty. Moreover, because the data are compressed, it's even less of a penalty when we actually talk about reading from storage, because we only read a fraction of the actual uncompressed data. In this case, the compression works out so that the actual size in storage is only about 20%. So this is right there a really big difference between ClickHouse and MySQL. Now, compression I mentioned, and I've sort of made a big deal of it. So I'd like to dig in a little bit and explain, just go through again how it works, as well as show you some examples of how effective it is. So in ClickHouse, we think of compression happening in 3 ways. One is it can happen through the data type, which by picking appropriate data types, they make the data smaller. It can also happen through a codec, which will transform the data before it gets compressed. And then it's finally, the last stage is always compression. And of course that will try and just, munge it down to something really tiny. So for example, we have a data type called a low cardinality string. And what that does is it says that, hey, if you're a string and you don't have very many of them, like airport names or something, we'll now store, instead of storing the full airport name, we'll actually do what's called dictionary encoding and just store an integer that then points to a dictionary that's held somewhere else that has the actual name. So we can do that, and then we can apply LZ4 compression, and that's one way of storing the data. Another one is for integers. Let's say we have a 32-bit integer. We could apply what's called a double delta codec, which means instead of storing the integer values, we store the differences of the differences of the integer values. So think of it, the slope of the slope. So if you happen to have an integer value that's slowly increasing, like temperature, for example, that's stored as an integer, what you're now storing is a very small number of bits, or maybe even 0 bits for each of these values. We turn that over to ZSDD and get it compressed. Here's some examples of how effective this can be. So for example, the carrier name, which is a short string, just if we do nothing, it gets compressed with LZ4, and the reduction is almost 95%. It's 5.64% of the data actually gets written, or size on disk. What's even better is if we take that carrier and we apply low cardinality, so turn it into this dictionary encoding and then put LZ4 on it, we get less than 1% of the data that's stored. This is an enormous compression. Flight date is even better. So the flight date with LZ4 compression, we do nothing but compress it. It turns out it's going to be repeated in every row because of the way we've designed our table. It's pretty tiny, but we can make it even smaller by using double delta plus the SDD compression. These are all examples of where you can get compression levels up to, in this case, 300 times. It's just an enormous compaction of the data, and this is one of the reasons why we can read these columns so fast. The last example just shows that nobody's perfect. So origin is the origin airport. We're not storing it very efficiently because I haven't tried to put a dictionary encoding on it and compress it nicely. That's one we'll have to go work on, but that shows you what you might get in some cases out of the box. So this is really sort of a huge decrease in the amount of I/O that you have to do. On top of that, what we can do in a data warehouse, and virtually all data warehouses do this, is they'll use more than one thread. So they'll distribute the query on, they'll grab as many threads as they're allowed to and basically run them on separate CPUs. This is an example of a query that's looking for late or delayed flights. And what I've done is I've just set this parameter which allows me to control how many CPUs I run on. And so I set it to 2, to 4, to 6, to 8, and then I run the query and you can see what the response is. If you'll see that as I go from 2 to 4, the response time drops by almost 50%. It drops off after that. As it turns out, this is actually a 4 CPU machine with a 4-core machine with hardware threading, so 2 hyperthreads per core. So part of that drop off is probably because we're now no longer able to use the threads as efficiently. Plus, there's also some aggregation and other things that go on here that have to be done in a single thread. But this just illustrates how easily we use the resources. And then, if that's not enough, this will do fine if we've got a human asking these questions and they can afford to wait a couple seconds. But sometimes we have applications that are asking questions. And if you want to pop something up in a browser, for example, you may need to make a decision on the back end in 10 milliseconds or less. In that case, what we use are materialized views to compact the data still more. And what they're going to do is we're actually going to pre-compute some of the aggregates, the questions that we might ask. And so the materialized view is basically like a trigger that when you put something into the source table, the materialized view runs a query on it and puts the results in a target table that you can then query. Here's an example. So I create a materialized view that actually asks that same question, but basically allows us to pre-aggregate some of the data. So we're going to just figure out what's the sum of canceled and delayed flights by flight date by carrier. So by doing this, I can now query this and I'll get a query speed up of something of up to 100 times. There are cases where this can speed up the queries by 1,000 or even 10,000 times. And one of the big reasons is it just drastically reduces the amount of data you have to scan because you've already answered the question and so it's not hard to get the answer. You're still not fast enough? Well, at this point, data warehouses, and ClickHouse is no exception, allow you to add more servers. So you can replicate the hosts, or replicate data across hosts, so a table can be replicated. Moreover, you can shard the tables. So you basically have what I often call disjoint sets. So you can divide the airline data up 3 ways, put 1/3 of it on one host, 1/3 of it on another host, 1/3 of it on the last host. And what that does, what the sharding does, is increases your read and write bandwidth. So it means that a query, you can run it now across all 3 hosts and it'll get dispatched to each of the hosts and then the results will get aggregated and passed back to you at the end. And the result, if you do it well, is really excellent. You basically get linear scaling. So the sharding and replication are built in. The replication is just a details if you're interested. It's multi-master with eventual consistency. And this is what I mean about, hey, if you're computing a bill, you could get cases where the counts are approximately correct, but could be inconsistent depending on who's writing in what order to which servers. But the linear scaling, there's no doubt of that. So this is an example in this graph where the blue lines are from a cold run where I'm forcing it to read from storage. And you can see that as I go 1, 2, 4, it basically drops off 50% each time. The hot runs are where we've allowed the data to come into memory and we're running and we still get, because there's still CPU time involved here, we still get linear scaling. So this gives you kind of an overview of why data warehouses are so powerful and why you might, if you're doing an analytic application, you would choose this as opposed to MySQL or another row store like Postgres, well, Oracle is not a good example, but sort of a conventional relational database. What I'd like to do now is, here we go. Yeah, so let's talk about strengths and weaknesses. So I'm very enthusiastic about Postgres, about ClickHouse. I like Postgres too. I love ClickHouse. But the interesting thing is the strengths of analytic databases tend to be the mirror image of MySQL. So we're great at long tables, so tables that run into trillions of rows, tables that have, you know, up to 1,000 columns, very open-ended questions for which you have no index, and then aggregates, which you can pre-aggregate and then answer very quickly, but you can also answer them quickly anyway if you're willing to wait a couple seconds. And ClickHouse can be, for these types of things, ClickHouse can be easily 1,000 times faster than MySQL. What it's not good at is cases where you have lots of lookups, where you have lots of updates, where you have very high levels of concurrency. ClickHouse, just to take one example, does not update data in real time. It will update it in the background. So if you're trying to add something to somebody's basket, it's not a good database to use for that. So I hope this gives you kind of an overview of some of the strengths and weaknesses. What I'd like to do at this point is just wrap up. And I think what's helpful is to just think about this in terms of applications and which one fits, which type of database fits in which case. So if you manage websites, you're probably really familiar with this picture. This is WordPress. I spend a lot of my time there on both at work and in side projects. And MySQL just shines for this. WordPress has a lot of little related bits of information. Consistency is really important. When people are hitting the website, you need to serve it. You need to go into MySQL, do quick queries so that you can build the pages and serve them up quickly. MySQL is excellent for this. And in fact, WordPress was one of the big drivers of MySQL adoption, because when it was originally written, it needed to have a database. They picked MySQL, and it just ran, it would work with MySQL out of the box. And so as a result, it's really great. Here's an example of a place where ClickHouse shines. So if you manage, once again, if you deal with websites, you're probably familiar with this. This is Google Analytics. And in fact, as I mentioned at the beginning, ClickHouse was developed to solve exactly this problem for Yandex Metrica, which is actually the #2 web analytics program after Google Analytics. And in this case, people are asking open-ended questions. So anything related to web traffic, combining it in different ways, sort of picking a primary dimension and then cutting it, picking sessions and then cutting them up by, where they're from or what the referrer is, all kinds of different combinations. ClickHouse is great for this. And all the properties I talked to are really, really, really powerful. There's a final question that this leads to, and then I'll get to your questions. Can one database do both of these things at once? And that's a question a lot of people have asked for many years, and the answer is, in my opinion, is not really. And I think there's a couple reasons for this. One is trying to do both of these things at once makes the database very complex. You really have to organize the storage two ways. That's a fundamental problem. You organize the storage two ways. You also process things in very different ways. Like in one case, you're optimized for very lightweight transactions. In another case, you're optimized for grabbing all the resources. So databases can, you can build databases that do this, but they're complex and hard to do. I think the more important thing is I don't think the market is really asking for it. And that is, if you go back and think of those applications, nowadays you wouldn't build like a big old hairy monolith that both manages your website and does the analytics. Maybe some people do. What you tend to do is have different applications that are focused on each of those problems. As a result, they can each choose a database that's appropriate for them. So with that, just a quick summary. So row stores like MySQL, conventional relational database, they're great for transaction processing. Doing e-commerce, running a website, doing anything that involves transaction processing, where you have lots of updates, small queries, and you need transactional integrity, MySQL is great. And databases like Postgres are just as good. Column stores like ClickHouse are wonderful for analytics. So tables that are wide and long, running into trillions of rows, asking open-ended questions, including, where people are just slicing and dicing the data, and then with lots of aggregated results. Sometimes, and these are questions that are often, for aggregates, often asked by humans, but equally often asked by applications who need a really snappy response. So that's the end of my talk. I just want to say, if you like this stuff, we're hiring. Particularly if you think, you think you can do this better than I did. Well, we'd like to talk. And here's here's a couple of links. MySQL is familiar to you. I'm giving a shout out to Percona that's Peter Zaitsev was doing a keynote. He's a good friend. And then ClickHouse source code is here. Feel free to send me email messages afterwards or check with me on Hoover. And with that, Nilesh, I'm going to jump over and answer questions. There was one that, okay, this is a great one. I'm going to take the second question first. What are the strengths of ClickHouse compared to other databases used for data warehousing? That's a great question and one that we get a lot. So what are the other options that you have? Cloud data warehouses are very popular, and so I'll just focus on those for a minute. The big ones are BigQuery, Redshift, and let's see, Snowflake, of course. Probably people on the call using them. They are so let's say why these databases are good. One is that they are have very complete SQL implementation. So you think about all the stuff that you want to do and use sort of all your standard tools. You want to have window functions and advanced analytic capabilities. All of these databases do this great. The other thing is they're increasingly serverless. So if you're looking for something where you just want to, you don't want to really have any connection with the, with the platform, and you also only want to be charged when you're actually running a query, they by and large, they all support these models. Redshift didn't used to, but it's changing. Where ClickHouse really shines at this point is one, portability. So it runs anywhere. Two, it is extremely fast. So this a pretty standard measure is with ClickHouse, you can apply enough resources and you can basically get queries for humans, slicing and dicing queries, you can get down to a second or on the order of a second. And then you can get response time for aggregates down to 10 milliseconds. Cloud warehouses simply don't do this. Those are two examples. What you do give up for ClickHouse, because there's no free lunch here, it does not have a full SQL implementation like the other databases I mentioned. So it's really good for low latency. It's really good if you want flexibility. ClickHouse, one final thing I'll mention is it runs great in Kubernetes. There is a cloud platform for it. We're building it. Yandex also has one. So you can find cloud platforms for it, but there's definitely some trade-offs here at this point. I hope that answers that question. If I want to learn more about data warehouse design and variations, would you recommend any sources for low cost or free quality learning information? That's a really great question. And actually a little bit of a hard one. I would recommend, I have to give kind of a shout out. It sort of pains me to do it. I have to give a real shout out to Redshift for the quality of the documentation and the dev information that they provide. That's a good place to look. So for particular products, for our product ClickHouse, we do rafts of webinars, so you can go and find out about using ClickHouse. As far as data warehouse design, that's a little bit harder. There are books about it. I've never found them tremendously satisfying. I think the best thing to go is just go out, get something like ClickHouse. You can run it for free on your laptop. Just try it out and you'll start to get the feeling for how you design these applications. Okay, I think we're at close to time.
We have a couple of minutes, so
yes.
if any further questions, guys, feel free to add it to.
Yeah, absolutely. And meanwhile, thank you so much for attending this talk. I hope it was useful, and I definitely hope that you'll be able to use this information when you're as you're designing your own applications.
Awesome. Thank you so much, Robert, for the presentation. I appreciate all the attendees for joining and their great questions. Please contact the speaker if you have further questions regarding this topic. Please also provide your comments and feedback to us or the organizers on the community board, or start a discussion there to connect with others in the DataCon LA 2020 community. Thank you again, everyone, for joining today's presentation. I hope you've gained some really useful insights from this session. Have a wonderful day, and thanks for being part of this year's DataCon LA.
Thank you. Bye-bye.